Hello, welcome back to AC Circuit Analysis. Here we're going to finally connect the dots. We're going to talk about complex power theory part 2. At the end of this lesson, you should have a really good understanding of why we've been talking so much about P and Q and complex power and things like that. When I tie it all up at the end, if you don't have an aha moment or an epiphany of, wow, that's really neat, then I probably haven't done my job right, and then I'll be really sad. So hopefully I can do a good job here. What we've talked about from the last section, I should say recall. All right, recall that complex power S we said was capital P plus JQ. Real part plus imaginary part. Average real power plus the imaginary part, which is just the reactive power. Now, we're going to substitute in for P and Q. So here's P and here's Q. We know what those quantities are as they relate to the sinusoid. So we're just going to substitute them in there. And where we're going is I'm going to show you that S, the complex power S, is a phasor quantity. And I've been kind of hinting that all along, but we're actually going to do it now. So when we substitute in, we will say that S is equal to, for P, remember the equation for P that we used a few lessons ago was the following. It's Vm Im over 2 times the cosine of theta V minus theta I. Okay, that is P. So this is basically exactly from a previous lesson. This is how you calculate the number P, the average real power. Plus, we're going to add to that, with a J there, we're going to put in what we know Q is equal to Vm Im. This is why we spent time before solving a few problems, just a couple of problems, finding P and Q manually. Sine of theta V minus theta I. All right, so this is essentially the complex power S. This is P, and this is Q, and this is all stuff from previous lessons. We're just kind of tying it all together. Now let's do a little bit of simplification. You see we have this term here, which is exactly the same as this term here. So we're going to factor those guys out and see where we go. S is equal to Vm Im over 2, and we'll open up a pair of brackets, and inside we'll have cosine theta V minus theta I. We'll have parentheses around that, plus J times the sine of theta V minus theta I. And we'll close the brackets off. Okay, so where we're trying to go here is to show you that this is basically a phasor. Now, here you have the very famous relation. Cosine of an angle, remember this is a difference of two angles, but effectively it's just an angle here, plus J times the sine of an angle. And if you remember, I'll put a recall off to the side here. Recall, this will be like a little aside here. The famous identity, e to the J angle is equal to cosine of the angle plus J times the sine of the angle. This is Euler's identity, and you probably haven't looked at this recently in circuit analysis, but if you go back to when I first introduced the concept of a phasor, this was actually critically important to defining what a phasor is. Because basically anytime you see cosine of something plus J times the sine of something, you can write it as a complex exponential like this. These are equivalent forms of exactly the same thing. You don't have to prove this. This is given to you by a famous mathematician named Euler a long, long time ago. But we can use that fact and stick it into here as follows, because now we can rewrite this and we can say that S, complex power S, is equal to Vm times Im. These are the amplitudes of the voltage and the current. Divide by 2, but instead of this enormous thing in brackets, we'll just write it as a complex exponential. E to the J theta V minus theta I. Now what does that look like to you? Well, this is just a number. This is a number times a number divided by a number. So what we have out here is an amplitude, right? And here we have e to the J and then a number. And if you go back and look at when we introduced the concept of a phasor, this is a phasor quantity. When you have an amplitude, e to the J, with some number there,